Welcome to Module 4. So far in this series of videos, we've learned about how computers represent and work with integers, about the logic behind how those and other computer operations work, and in Module 3 we learned about sets and functions, which are the prototypes for computer data structures and programs. All of that material lays the groundwork for what the next two modules are about, thinking mathematically about underlying problems that show up throughout computer science. One of the major categories of those kinds of problems is counting. I don't mean simple counting, like you learned when you were a toddler. We mean counting complex arrangements of things. For example, how many 16-bit strings are there that have exactly 10 one digits? Or if your computer password has to be a 12-character string that must contain a number, a capital letter, and a special character, how many passwords are possible? Or if you're trying to sort a long list of numbers or words, how many steps are needed? The particular area of mathematics that deals with counting complex arrangements of things is called combinatorics. Combinatorics is central to computer science for many reasons. Maybe the biggest reason is that before we write code on a computer program, we first of all have to understand the underlying algorithm that we're trying to implement in that code. And part of that understanding resides in how many steps or computations are needed. For example, going back to sorting, if we're given a long list of numbers or words to sort, then there are some ways of sorting them that are more efficient than others, because although different methods may give the same result, some take less time than others and scale up better for longer lists than shorter ones. To be able to understand the efficiency of algorithms, we need to be able to count the steps. So this module is an introduction to the basics of combinatorics, and I hope that as we work through the ideas here, you will not only see their usefulness in computer science, but also that you'll be impressed by just how cool and beautiful some of these methods for counting complex arrangements are. Let's begin with a basic problem that we literally encounter every day: choosing clothes to wear. In my room at home, my shirts are put in a few different places. The long-sleeve dress shirts are on a rack in my closet, and short-sleeve dress shirts are on another rack in the closet. These are two separate locations for my shirts. Now, let's suppose I'm getting ready for work and I need to pick a shirt. If I have 6 long-sleeve shirts and 10 short-sleeve shirts, and if these are the only shirts that I have, then how many possible ways can I pick a shirt? So visualize my shirt arrangements like this, where the shirts live in separate bins. My room doesn't actually look like this, but the drawing here is an abstraction that represents these bins. Importantly, these bins don't overlap. There is no such thing as a shirt that is both short sleeve and long sleeve at the same time. Well, if I pick one shirt, then there are 6 possible choices from the long sleeve bin, but I also have 10 possible choices from the short sleeve bin. So in all, because it's just one choice and neither of these bins overlap, that's 16 possible shirt choices. That's all my shirts, and each one lives in one, but not more than one, of these bins, and I am just picking a single shirt. What we just illustrated is something called the additive principle of counting. The additive principle says that if an event called A can occur in M ways and another event B can occur in N ways, and those events are disjoint, then the event A or B can occur in M plus N ways. Let's unpack the language here. First of all, an event refers to the outcome of an action. So in our example, choosing a shirt is an action with 2 possible events as outcomes. Event A is I picked a long sleeve shirt, and event B is that I picked a short sleeve shirt. And when we say 2 events are disjoint, we mean the same thing as when we say 2 sets are disjoint. They have no intersection or no common elements. 2 disjoint events are events that can't both happen at the same time, like picking a shirt that is both long sleeve and short sleeve. So in our case, I'm making a single choice that has 2 disjoint outcomes. Or you can think of it as I am making a single choice by picking one thing from 2 disjoint sets. The additive principle says that in these conditions, the total number of choices is just the sum of the possible outcomes over each bin. Here's another example. I also have 20 t-shirts in a drawer in my room. 6 of those are black, 4 are green, 8 are blue, and 2 are white. None of them are multicolored. If I don't want to pick a dress shirt, either long or short sleeve today, but a t-shirt instead, how many ways are there to pick either a black or a blue t-shirt? Pause the video and work this out. The additive principle applies here because we're making a single choice that has multiple disjoint outcomes. Again, I don't actually keep the t-shirts in separate drawers, but you can think of it as separating the different colors into different bins and making one choice from among the bins. And again, note that none of the shirts are multicolored, so all the bins are disjoint. The number of ways to pick a black shirt is 6, and the number of ways to pick a blue shirt is 8. So the additive principle would say that the total number of ways to pick either black or blue is 8 plus 16, which is 14. Now let's make this a little more complicated. Suppose that not only my t-shirts, but also my long and short sleeve dress shirts have colors. Remember, there were 16 dress shirts in all. Let's say that 8 of those are white, 5 are pink, and 3 are blue. If I were going to pick a single shirt, and it can be from any of the shirts I own, long sleeve, short sleeve, or t-shirts, then how many ways are there to pick a shirt that is either a t-shirt or is colored blue? You might answer by saying there are 20 t-shirts. And looking at the blue shirts, there are 3 blue dress shirts and 8 blue t-shirts for a total of 11 blue shirts. So the additive principle would say there are 20 plus 11, or 31 ways to pick a shirt that's either t-shirt or blue. But this is incorrect, and here is why. There are definitely 20 t-shirts, and so 20 ways to pick one. There are definitely 11 blue shirts, and so 11 ways to pick one of those. But there are 8 shirts that are both blue and a t-shirt. So when counting the number of shirts to pick, those get counted twice, and so the number 31 is too big. To correct it, I need to subtract off the number of shirts that are both blue and t-shirts, because again, I counted those twice when I added, so subtracting that number off once will result in counting those shirts only once. So the real number is 20 plus 11 minus 8, for a total of 23 ways to pick a shirt that's either blue or a t-shirt. The reason that the additive principle didn't apply here directly is because the bins aren't disjoint. The two events or outcomes of my choice, either a t-shirt or a blue shirt, can overlap because there are some shirts that are both. So instead of the additive principle, we're using a simple version of what's called the principle of inclusion and exclusion. It's phrased in terms of sets and cardinality. This cardinality of a finite set A union with another finite set B is the cardinality of A plus the cardinality of B minus the cardinality of the intersection. This is just what we saw in the example. A was a set of t-shirts and B was a set of blue shirts. And A union B is a set of shirts that are either t-shirts or blue. That number, the cardinality, was the number of t-shirts plus the number of blue shirts minus the number of blue t-shirts, because if we simply added the first two numbers, the intersection gets counted twice, so subtracting off one intersection corrects that count. Notice that if A and B do happen to be disjoint, like in our very first example, then the formula here gives an empty intersection, which has cardinality 0, and that gets us back to the basic additive principle. We'll be returning to the principle of inclusion and exclusion later in this module to deal with complexities that come when you have 3 or more sets of objects that you're choosing from, where there are 2-way and 3-way intersections at work. So in this video, you learned about the important field of combinatorics and why it matters to computer science, the additive principle, which tells you how to count the number of ways to make a single choice from a disjoint collection of bins, and the basic principle of inclusion and exclusion, which counts the number of ways to do this if you have 2 bins that aren't disjoint. Next up is a counting principle that goes with these for how to count multiple choices.